for the F4, I should draw like this. So this extension for the arrow mark for force F4 can be called as the line of action of force. Then if I draw a perpendicular, so this is a perpendicular direction for both the line of action of the force. This intersection can be named as N. If this is a normal direction, so the normal is drawn like this, but magnetic field is moving in this direction. So theta is the angle between normal drawn to the area of the coil and the magnetic field. So automatically, and this is the angle of this particular structure. Now considering that PSN as a triangle, so in the triangle of PSN, and you can calculate sin theta. Sin theta is opposite side by hypotenuse. So PN by and PS. What is PS of this coil? PS, look at the main diagram. The PS gives the breadth of the coil. So it becomes a B. So the PN is a perpendicular distance between the two line of action of the force acting on the coil. PN is equal to B sin theta. Now you can substitute this as a perpendicular distance in the torque formula. So torque is equal to BIL into PN, which is equal to BIL into L D sin theta. So for a rectangular coil, when you multiply L and B, will give you the area. So L into B will give you the area. So tau can be written as BIA sin theta. So this is a basic formula for calculating the torque experienced by the rectangular coil placed in a uniform magnetic field. But if a coil has n number of turns, then you have to add n, then you should say that coil torque experienced by the coil having several number of turns placed in a uniform magnetic field can be NBIA sin theta. See, look at that, theta is there. Now look at the theta. Theta is the angle between normal drawn to the area of the coil and the magnetic field. So if you take that, the eraser as a coil. When you place the plane of a coil parallel to the magnetic field, the normal drawn to the plane of a coil is perpendicular to the magnetic field. So whenever plane of a coil is so parallel to the magnetic field, then the torque experienced by the coil will be maximum. Suppose if you place the plane of the coil perpendicular to the direction of the magnetic field, assume that the marker shows the direction of the magnetic field. So when the plane of a coil is placed perpendicular to the direction of the magnetic field, what happens? The angle drawn to the normal to the coil is 0 with the direction of the magnetic field. So sin 0 becomes 0. There won't be any torque experienced by the coil. So whenever the plane of a coil is parallel to the magnetic field, the torque experienced by the coil will be maximum. When it is perpendicular to the coil, when it is kept perpendicular to the magnetic field, the torque experienced by the coil will be 0. The next we will move to the moving coil galvanometer. So moving coil galvanometer is a device that is used to calculate the current. And when you just go through the construction part, I would like to just show the diagram. So look at the book and you can see the diagram. So this is a construction part of a construction part. A rectangular coil contains large number of insulated wire wound over a coil suspended with the help of a phosphor bronze wire. And this, when you look at the top end of the phosphor bronze wire, a mirror lamp attachment with the light is fixed. So when you pass the current through the coil, just now we have seen that any rectangular coil will experience a torque. So due to the torque, this coil will turn and deflection can be produced. The deflection is produced by the coil. The amount of a deflection can be measured with the light deflected or reflected from the mirror attached on the suspended wire. And the entire coil is actually placed in the horseshoe pole pieces of the magnet. You can see the horseshoe pole pieces of the magnet. Here is a north pole and a south pole. And this particular field, so here this particular field will produce a radial magnetic field. So whenever a coil is placed in the radial magnetic field produced by the north and the south pole, we can able to achieve that the plane of a coil is so parallel to the magnetic field. Then only the torque experienced by the coil will be maximum. In order to achieve that, the maximum torque, the radial magnetic field is produced by placing that horseshoe shape of the magnetic pole pieces. And then the top end of a bronze, phosphor bronze wire is fixed onto the torsional head, which can be movable. And the bottom of the coil is placed on the hair spring that is also made up of a phosphor bronze combination and which has a few turns. Now, when you pass the current, what happens? As we have seen, a rectangular coil carrying current placed in a magnetic field will experience a torque. Now, I am going to draw the coil structure to make you to understand how much amount of a torque is produced. So, the torque can otherwise be called as a moment of a deflecting couple. So, the moment of deflecting couple, namely tau, is equal to one of the forces into perpendicular distance. So as you know that this is a shape of a circular coil, the corners of circular coil namely P, Q, R, S, but force experienced by this side and top side and bottom side are getting cancelled, and the force experienced by this left hand side namely P and Q is acting towards the outward direction, and this goes in inward direction, as you have already known that. So because of these two forces, namely this also F3, this is F4, inward and outward, making the torque to turn, and that will produce a moment of a deflecting couple called tau. So we have already studied that this force is nothing but Bill, and this is also, you see, this Bill sign Bill. So we can use the one of the forces as a Bill. But what is a perpendicular distance? See, draw a PS, the top force of this rectangular coil separately, and the F3 is acting outward and F3 is moving inward, and the breadth of the coil itself acts as the perpendicular distance. The breadth of the coil acts as a perpendicular distance. So you can say that the PS as a perpendicular distance, which is nothing but the breadth of the coil, so which is into the PS. The PS is the breadth of the coil. So the moment of a deflecting couple tau is equal to BIL into P. So whenever coil actually carries a current, this is turned because it's suspended by a phosphor bronze wire. So automatically the couple, a twist, is produced in the suspended wire. That twist produced in the suspended wire is otherwise called the moment of a deflecting couple. You have already studied in 10th standard, 11th standard, that is, while you studied the angular harmonic oscillator, the deflecting couple can be said as C into theta. So the deflecting couple, which is also referred by torque, and the tau is equal to C theta. By the quantity wise, the moment of a deflecting couple and a restoring couple, this is called a restoring couple, the moment of deflecting couple and a restoring couple are equal in quantity. So we can equate C theta is equal to BI. So the L cross B is nothing but area. So we can say that BIA. If the coil has n number of turns, we can write NBIA. So this is the final expression for the moment of a deflecting couple called torque, and this is the expression for the restoring couple in the name of twist produced in the suspended wire when the coil turns. So point divides they are equal, I am going to equate it. This is nothing but NBIA. So our aim is to, because the entire moving coil galvanometer is used to calculate the amount of the current which is produced.